Between 1980 and 2018, there had been 28 flood events, caused $123.5 billion losses, and at least 543 direct casualties in the U.S. Therefore, increasing resilience and disaster risk reduction are central to alleviating financial losses and boosting shared prosperities. However, hazards do not need to become disasters. Flood events can be predicted and flood hazards can be mitigated before becoming life-threatening and money-costly disasters. But how can we do that? Flood inundation models can help us do so. It can predict flood events and provide guidance in flood planning decision-makings. And those models can help planners evaluate trade-offs between proactive and reactive approaches so that flood planning can be executed at the most efficient way. To build a model, we take an approach that is different from the conventional method, such as the one used by HackRES. In terms of our approach is to construct a predictive model for flood inundation based on actual flood events observed. And the model takes factors, include but not limited to hydraulic characteristics, into account. By considering built environment factors, our model is more holistic and better fits the complex nature of urban environment. So how do we predict flood events? We took the city of Calgary as our study area, split it into a grid, and classified whether or not there were any floods during the 2013 flood event. Given that we are predicting for one of two likely situations, we used a logistic model. Based on the model results, we can calculate the probability of a flood event for each of our grid cells. We then define a cutoff probability value that determines if a flood event occurred for a grid cell. To stay on the side of caution, we choose a conservative low value for this cutoff to minimize the rate at which actual flood events were not identified. In order to predict, we selected natural, hydrological, and built environment features. We removed features that are significantly similar to another. And in the end, our model worked best with these four factors. All were significant predictors. Overall, our model is pretty accurate. We correctly predicted whether or not there were any floods in over 91.4% of Calgary. Our model performs really well at identifying sites that did not flood, predicting 97.2% of actual non-flood events. Although not as well, our model still predicts 78.2% of actual flood events. Based on the map, it can be observed that the model best predicts actual flood events that occurred close to the river. However, for floods occurring away from the river or along thinner streams, our model either does not identify such events or predicted floods in slightly adjacent areas. The high accuracy performance didn't vary when testing our model on 100 different subsets of the data, that it is generalizable as a whole shown on the left graph. Here, the accuracy rates are consistently high. However, the accuracy rate vary widely between neighborhoods, meaning that it is spatially biased. The model is less accurate for neighborhoods located near the river. When applied to Philadelphia, a city which faces flood threats from both the Schuylkill and Delaware River, the model predicts similarly well. The conservative approach we took results in high false positive rates for the outcomes of the model, indicating that unnecessary investment would be made in the areas that would not flood. Therefore, for the next step, we suggest the model should be further improved by testing on different flood events to evaluate its temporal and geographical generalizability, and to test different cutoff points to see the trade-offs between different models and provide insights in the economic and social impacts in taking proactive or reactive approach. Lastly, we should incorporate more features into the model, such as level of flood mitigation infrastructure, so that the model could be further optimized.